Hello. So, welcome to the week 5 live section of the NPTEL course Design of Reinforced Concrete Structure. I am Sanjay Kumawat, and today we will be solving a total of 3 questions, and all of those questions would be on the design of shear reinforcement for a beam. So, let's begin with today's session. Okay, so let's first discuss what we will be doing today in very brief general case. So what we have seen up to now, suppose this is a beam and this is a UDL, that is a combination of dead load and a live load which is acting on the beam. So what all are the stress resultants which we normally do or which we normally analyze for this beam? What we have is we have a bending moment diagram. And what is the other one? The other one is we have the shear force diagram. So this is the bending moment and this is the shear force. Okay, so up to now what we have done, we have analyzed our beams for the amount of bending moment acting on the beam. So whatever was the bending moment, for that bending moment, our for our beam to resist this bending moment, we have designed the reinforcement into it. So for this case, what we have done, we have seen two cases, that is firstly is the singly reinforced beam, the other one being the doubly reinforced beam. So this design was to incorporate the bending moment into the beam. But what about the shear force? Now in this session today we will be seeing how we are incorporating the amount of shear forces which are coming onto our beam, how our beam will resist these shear forces. So first of all, we should know that for the design of beam, for the amount of shear forces which is coming on it, we are considering the nominal shear stress. We are not considering the true shear stress. Why? Just for the case, for the purpose of simplicity, we are considering the normal shear stress. And what is normal shear stress? Normal shear stress for prismatic beam, it is nothing but the ultimate shear force which is coming onto this beam divided by the area of cross section. And in that area of cross section, we are taking the effective depth of beam. So this was the nominal shear stress which is acting up into the beam. And now this was the load which is coming onto the beam. This was the shear force which is coming onto the beam. Now what about the shear resistance? So when we talk about the shear resistance, the shear, it is mainly resisted by two components in the beam. So what are those two components? Firstly is VUC. What is VUR? VUR is nothing but shear resistance of beam at ultimate state. VUC is shear resistance of the concrete. Okay, so it's very easy. What is it? The shear, it is resisted by firstly by the concrete itself, and the second one is the stirrups. What are stirrups? You must be knowing it, and I will be explaining you this in just a while. So first let's see at VUC. So what is VUC? VUC is nothing but the shear force which we are getting from the concrete itself. So concrete as a material itself is has some shear resisting properties. This shear resisting properties, this VUC, it actually has three components. First one being the shear resistance of concrete, second one being the shear resistance provided by the aggregate interlocking, and the third one being the shear resistance because of the provision of dowel bar. So dowel bar are nothing but the tensile reinforcement which we have provided. So these three components, all of them contribute to VUC. Okay. So what I said, VUC, it depends upon the concrete. So it's very obvious, like for the value of VUC to be known, what we should know, we should know the FCK, that is the characteristic strength of concrete or the grade of concrete. Second one is what the important second one factor is. V aggregate, it also depends upon the concrete itself. V dowel is what we should also know the amount of reinforcement which is provided into the tensile zone. So for the calculation of VUC, what I will need firstly is the VFCK. What is the second one I need is I need the amount of reinforcement, that is percentage of reinforcement in the tensile zone. So these two factors are required in order to find the shear resisted by the concrete itself. Now let's look at the other component. What is the other component? Other one is VUS. So what is VUS? So let me explain you this. I hope VUC is clear to you all. Now, what is VUS? Okay, suppose this is my longitudinal uh, axis of my beam. Okay, so you all must be knowing that when shear forces acts on beam, what generally happens is it produces some cracks like this. So maximum shear force occurs at a crack of 45 degree, and when the crack is vertical and just below the load, what we say, this is a flexural crack, and this is the shear crack. In between these two cracks, if we have some other crack which is at some other angle, what we say, this crack is generated because of both flexure as well as shear. So to take care of these flexural cracks, what I do, see, this is, you can visualize it. Suppose this is the shear crack. So what I did, shear crack means what, this beam will try to like separate into two parts. So what I did, I simply provided tensile reinforcement at the bottom. So this tensile reinforcement will take care of this flexural crack. Now, to take care of this diagonal crack, what will I have to provide? I will have to provide what? I will have to provide stirrups. So these are all our stirrups. Okay, so these are the stirrups, and here the total shear resistance of the beam, it is a combination of VUC, that is the shear resistance of concrete, and VUS, that is the shear resisted by the shear reinforcement which I have provided. So let's look at the slides. What does it says next? Okay, so VUC is shear resisted by concrete and the tensile steels, and that is the reason I said you it depends upon FCK and the percentage of steel. Let me erase this one. Okay. Okay, so what's next? VUS is shear resisted by stirrups, and VUC depends upon the grade of concrete and the area of longitudinal bars. And how to calculate it? We have a table in IS 456, table 19, page 73. We can easily calculate the design shear strength of concrete, that is tau C, based upon the grade of concrete and the area of tensile reinforcement present in that beam. So let's move on further. What do we have further is VUR limit. Okay, so what is the ultimate failure of a beam in shear? So when a beam, as we know, it is made up of concrete, and concrete, it has a very poor behavior when it is subjected to diagonal compression. So when a beam is subjected to diagonal compression, what will happen? It will lead to a brittle failure, which is the failure of concrete all of the sudden. Okay. So VUR limit, we have to limit the shear resisted by this beam to VUR limit. Why? Because if this failure occur, irrespective of what shear reinforcement we have provided into this beam, our beam will fail. Okay. So whatever amount of reinforcement you provide into this beam for shear resistance, all those shear reinforcement are useless if the resistance it falls greater than VUR limit, because it has to fail. This failure is brittle failure, and we do not want our beam to fail all of the sudden because of diagonal compression failure. So this should be taken care of, like whatever the shear resistance of our beam is, it is less than VUR limit. Okay, and how do we calculate VUR limit? Also, we have a table in IS 456 based upon the grade of concrete. Now, can any one of you tell me why the design shear strength it depend upon the grade of concrete as well as the percentage of steel? And when we talk about the VUR limit, that is the TOSI max. When I talk about TOSI max, sorry, when I talk about TOSI max, it depends only upon grade of concrete, M something. Okay, but when I, in the previous slide, when we saw the design shear resistance of the concrete, it was depending upon percentage of steel as well as the grade of concrete. Why is that? Can any one of you answer me? O- okay, okay, so that was a correct answer, but to be more precise, what did I say to you? TOSI max, that is when a beam is having a failure due to diagonal compression, that failure is a sudden brittle failure, and that failure is irrespective of any amount of steel you provide, whether it is in shear, whether it is in shear reinforcement or it is the tensile reinforcement. Irrespective of any of the reinforcement, the beam has to fail if the shear acting on the beam is greater than the VUR limit. Okay, that's why it is not depending upon the area of steel. Diagonal compression, it usually acts at this point, like this. It is a brittle failure. It is under compression loads. 45-degree, sorry, there is an echo, I think. Okay, 45-degree, it is usually for the shear cracks, and those shear cracks, we for that shear cracks to take into consideration, we are providing the shear reinforcement. But we cannot do anything about this diagonal compression failure. Okay, you can say it can be at any angle, but to be more precise, for this we are providing the reinforcement, and diagonal compression failure, it is mainly because of the compression loads, and it can occur at 45-degree or at any other angle, but it is mainly due to compression. Mhm. Yeah, I know what. Yes, yes. So mainly the shear, it is, sorry, the principal shear or the maximum shear, it usually occurs at 45-degree. That's what you are trying to say. Yeah, that is the correct. So for maximum shear, it usually occurs at 45-degree, and that is the reason we have diagonal cracks like this. That is fine. Okay, you can relate with that only. That also not only. Okay. So moving on further, now let's see how do we provide the shear reinforcement. So shear reinforcement, first of all, they are mainly classified into two types, or I can say they are classified into three types. Firstly being the vertical stirrup, secondly being the inclined stirrup, and third one being vertical plus bent up bars. Okay. So here I am deriving the formula or formula. Let's first tell you that what does this provision, or how do we provide these stirrups, or what is the procedure of providing these stirrups. So these stirrups are mainly provided in the form of spacing. Okay, so you all know we have studied the provision of flexural reinforcement at the bottom and at the top. Those flexural reinforcement were provided in the form of AST1 and AST2. But here, please remember the stirrups, they are provided in the form of spacing. That is, we are deciding what will be the spacing between the two consecutive stirrups, and based upon that spacing, we are providing stirrups throughout the beam. And also depending, like if you are a good designer, what you can do, you can provide closely spaced stirrups near the supports, and the spacing would be more in the middle of the beam. Why is that? Because we know when we look at the shear force diagram, shear force is dominant at the supports. That's why. So it's fine if you even provide this small spacing throughout, but to be on the economical side of the construction, what we do, we are tend to provide less spacing at the supports and more spacing at the middle. Okay. So you just remember this thing. To provide stirrups, we should know at what spacing we should provide the stirrups. Okay, so you all know the classification of stirrups now: vertical, inclined, and with bent up bars. Now let's also look at how stirrups are provided. So stirrups can be either two-legged stirrup. This is a two-legged stirrup. Stirrups can also be three-legged, and stirrups can also be four-legged. In the cross section, you can see its leg, these legs. Okay, so normally on the construction sites, we intend to provide two-legged stirrups because of its ease of construction. So now let's see how do we find this spacing SV. Okay, so I know this is, you can directly also remember the formula of spacing, but it is also important to know how do we arrive at these formulas, because everything has some meaning, and those meaning actually helps us to visualize how failures are occurring and how we are resisting this failure from occurring. Okay, so suppose this is the beam and these are the inclined stirrups. Okay, let me switch on my laser pointer. Okay, so this is a beam and these are all the inclined stirrups. And suppose this is the crack which is occurring at an angle of theta. Okay, and and what is this? This is the angle alpha which is made up by this inclined stirrups. Okay, and this is the crack. Okay, so this crack, this crack, it is it is prevented by how many of the stirrups? One stirrup, two stirrup, three stirrup, four stirrups. Okay, and this crack is occurring at a angle of theta. Okay, so let's see how do we arrive at the formula. So 0.87 Fy ASV is the total force which is acting up into this bar, and this force, it is distributed among one, two, three, four number of bars. Or should I count it in this way, or should I have a better way of visualizing this, because I don't know what can be the number of bars in other case. We should have some generalized formula. Okay, so how do we get this generalized formula? Consider this triangle and look at the tan theta part. What is tan theta? Tan theta will be d upon, suppose this is x1 and this is x2 upon x1. Okay, what is tan alpha? Tan alpha will be d upon x2. Okay, so within this cracks, what will be our number of stirrups? Okay, what will be the total number of stirrups? Total number of stirrups would be nothing but x1 plus x2 divided by sv. Are you getting me? So what is x1 plus x2? From these two, substitute these values. What is x1? X1 is d by tan theta plus d by tan alpha. So I can take out the d and write it as cot theta plus cot alpha. Okay. So now what is this? What is x1 plus x2 by sv? This is the number of stirrups. So this is the force in one stirrup. When I multiply this by the number of stirrups, that will be the total shear resisted by the stirrups. I hope this was clear to all of you. If you have any doubt, you can ask me. Oh my god, what does this did I do? Okay. So, okay, this is the formula which I had derived just now. Sorry for this mess. I hope how did you all understood how I came up with this formula. So this was the case for inclined syrup, and now when I put theta equal to 45 degrees, then I get this modified formula. And this was the alpha, it usually comes up for what? The alpha, it comes up for the inclined stirrup case. But when I talk about the vertical stirrups, my alpha will be what? 90 degree. So at 90 degree, what formula I will have? I will have only this formula, 0.87 Fy ASV d by SV. So this is the shear resisted by the stirrups. Okay, so just remember, shear, it is mainly resisted by the concrete as well as it is resisted by the stirrups. When we talk about the stirrups, we should know at what spacing the stirrups are provided. And when we talk about the shear resisted by the concrete, we should know what is the grade of concrete and what is the amount of reinforcement. And what is the main part we should take care of is we should take care that the amount of shear which is resisted by the combination of stirrup as well as concrete, it should not exceed VUR. Okay, so now this is the one of the important discussion I am going to do. like you all know, we have designed beam in our previous section, and what we have saw like if my if my design bending moment it exceeds the moment of resistance of my beam, I provide doubly reinforcement, or the other method would be what I will do, I will be going for singly reinforcement but with higher depth. Okay, so these are the two cases or the two things what I do when my moment of resistance is less than the design moment of resistance which is coming onto the beam. But now in shear also there can be a case where we need to redesign my session. So to when that case will come, that case will come when my tossy into BD, this BUR is less than what shear is coming on my beam. So if UR is greater, or no, if UR is less, then what should I do? I should redesign my beam. I should provide a higher depth or a higher value of beam. I hope you are understanding what I am saying. There can be a redesign in case for the flexural case also, and there can be redesigning case in shear also. In shear, if my limiting moment of not moment, sorry, if my limiting shear resistant, that limiting shear resistance is less as compared to what shear is coming onto that beam, then there can be chances like I have to redesign, that is I have to take higher value of section. Okay, so I hope I was clear. Now let's look at some problems on all of these concepts that will make, like whatever I have explained you here verbally, now we will be solving it in the coming 3 examples. So what the first problem says, it says a rectangular singly reinforced beam is supported on two 230 mm thick masonry walls and 6 meters center to center. The beam properties and the flexural reinforcement are this, and this. There are 4 bars of 20 mm diameter. We need to design the shear reinforcement if the beam carries a live load of 40 kilonewton per meter. Assume M20 concrete. Okay, so let's look at the solution. Firstly, what we need to do, we need to determine the factor. Okay, so in any problem, what we have to first do, first we know that they have given a beam. This is the beam. It has some length of 6 meters center to center. Now, what they have given a live load of 40 kilonewton per meter, but we are not aware of the dead load. But for the dead load, they have given us the cross section. So from the cross section, I can calculate the dead load. So for the dead load, firstly, what we will do, what we will do, we will multiply it by the unit weight of concrete. Okay, so now what we are doing, firstly we are finding the effective depth. This we have done in the previous class also. So this is from the IS code provision. Center to center it is given as 6 meter, but we have to take the minimum of the clear span, or clear span minus the support plus the depth of concrete. So I have taken it as 6 meter. Now next, the distributed lead load, I have multiplied the unit weight of concrete with the cross section dimensions, and I got this value. Next is I have calculated the factored load which is acting upon this beam. So I got 65.2 kilonewton per meter. Now let me also explain you this concept. Suppose these are the masonry walls on which my beam is resting. Okay. So if I talk about this will be Bs by 2, that is 230 by 2. 230 is this. And my critical shear, it occurs usually at 45 degree from the support. So if D is the depth of the beam, and when I take tan theta, this distance will be also D. So my distance of critical depth of neutral, sorry, not neutral axis. So the distance where my critical section for shear it occurs, it is Bs by 2 plus D. So that's for here I have mentioned that. So 230 plus D is nothing but 500 plus 230 by 2 is 615. Now I know this is the total load which is acting on my beam. What is the total load? Total load is 65.2 So this is what WL by 2, WL by 2, and my critical section, it is at a distance of 615. So I have to calculate the shear at a distance of 615 mm from the center of this load. So I have done that for you. So WL by 2, I explained you WL by 2 at this section minus this load. This load is WU into X critical. X critical is BS by 2 plus D. Okay. So now this is the shear for which I have to provide the shear reinforcement in the beam. So shear reinforcement, I know the total shear which is resisted. It is equal to VUC plus VUS. So VUC, what is the total shear reinforcement I have to provide for? I have to provide the total shear reinforcement for this value. So firstly I have to calculate VUC. VUC, it depends upon FCK and the percentage of steel. So from IS 456 I can calculate VUC. Then I have to make sure that the VUC value or the VUR value, it does not exceeds the VUR limit. I have to make sure that also, because if it exceeds, there is no purpose of providing the stirrups. Irrespective of any stirrups I am providing, my beam will fit. Okay, so let's look at the slides only. So this is the Thomas. Okay, so this is the limiting. So I have seen that the limiting shear resistance, it is greater than my the shear which is acting on the beam, so it is fine. My cross section would remain safe. Now let's calculate the ultimate shear resistance of the concrete, which depends upon what? It depends upon the percentage of steel and the grade of concrete. So the percentage of steel, we have 4 bars of 20 mm, I think. So I got 1% steel, and from this table I know for 1% of steel and for M20 grade of concrete, what is my TOSI? It is 0.62. So what is TOSI is 0.62. So what will be VC? VC will be 0.62 multiplied by VD. Okay, so multiplied by VD, I have done it. So what's next? I calculated the shear resisted by concrete. Now I will get what, for what amount of shear should I provide the shear reinforcement. So this is the amount of shear for which the shear reinforcement is to be designed. So now how to design the shear reinforcement? This is all your choice. Here I am selecting two-legged stirrups. Two-legged stirrups. I am selecting this two-legged stirrups. So two-legged stirrup, it will be having an area of this d, I am taking it as 10. So for this two leg stirrup, what will be my spacing? I am calculating it as 218. So 218 is the required spacing, but I will be providing lesser spacing that than that value. So if we provide lesser spacing, that would be on again on a safer side. So provide two leg 10 mm stirrups at 200 mm center to center distance. So this is my, this I have completed the provision of stirrups for the coming shear forces. Now I have to also give some checks on this, whether this shear reinforcement made up my the maximum and the minimum spacing of this shear reinforcements which is provided, which is given in IS 456. Minimum shear reinforcement check, firstly I have given up here. So by the area of steel which is provided, it should be obviously greater than this minimum shear reinforcement. If it is not greater, then I will be providing this ASV value. So I have calculated it for you here. ASV minimum is 92, which is less than the ASV. So the area of steel which I am providing, it is greater. So that's fine. Okay. Now the maximum shear spacing, it should be less than this value. Okay, the maximum shear spacing, it is 0.75 by D and 300. So 0.75 into D, how much it comes? D is 500. So this is 375 and this is 300. So the minimum of this value should be our maximum spacing. But the spacing which we have provided is even less than this value, that is 280. So all my checks are satisfied. So in this way, I am providing my two-legged stirrups which are at a center to center spacing of 200 mm. So this was all about the first problem. Now let's move on to the second problem. What does it says? A rectangular beam of 250 mm width and 500 mm effective depth is reinforced with 4 bars of 25 mm diameter. I'm sorry. Okay. So what does the question says next? Using M20 concrete and Fe 415 vertical stirrups, determine the required vertical shear reinforcement to resist the factor shear force of first is 80 kilonewton, second is 300 kilonewton, and the third case is 600 kilonewton. Okay, so these are the shear forces for which I have to provide the shear reinforcement into my beam. And beam cross section it is already given. So there is no need to find what is the dead load, what is the live load. Here they are already asking me to design the shear reinforcement, or what they are asking. They are asking me to determine the required vertical shear reinforcement. For the first case is 80 kilonewton, 300 kilonewton, and 600 kilonewton. So this they have given what they have given VUR. So now firstly what I will do, all the steps remain the same. Firstly what I will do, I will find VUC. What is the shear resisted by the concrete? Then I will find VUS, that will be VUR minus VUC. Okay. So now I will ask you all one question. So first case is 80 kilonewton. Suppose my VUC is greater than 80 kilonewton. So what will happen? Anyone? The shear resisted by concrete is itself greater than the load which is coming on the beam. Yeah, yeah. So normally there is no need of any provision of shear reinforcement, but what IS 456 says, we need to then also we need to provide some minimum shear reinforcement so that if any accidental load come onto our structure, then that load would be taken care of by this minimum shear reinforcement. So now I think now you all are getting familiar up with this question. What does this question want us to do? See, in the first case, firstly what I will do, I will find the VUC. So, okay, now yeah, this is also important. Firstly, we need to find whether the shear which is coming onto the beam, whether it is under the limits of the maximum shear which can be resisted by the concrete to avoid the brittle failure due to the diagonal compression. So here I have TOSI max, which is 2.8 MPa, and I have multiplied it by the cross section. So I got this is the ultimate value of shear which the beam can take. So all of this load for which I have to design the vertical stirrups, all of these loads are less than 350 kilonewton. So okay, so all of them not. The case three it exceeds the value 350. So what will happen for the case three? Even if I provide the minimum or maximum any amount of stirrup, if I provide for the case C, my beam is definitely going to fail. So what comment should I give to the project manager? What comment should I give to him? Yeah, I will just say him, please go and redesign the section because this section won't be able to survive under the action of such high shear force which is acting onto this beam. So I we have already solved the case C. Now let's look at the case A and case B. So I will find VUC first. So percentage of steel is, here I have given 4 bars of 25 mm and the grade of the concrete is M20. So from that table you can easily find the TOSI. That table I have already shown you, and just please remember, if the percentage of steel, if it falls in between any of the two values, then please go for the linear interpolation. You can do that and find the value. Now my TOSI, it comes out to be 0.7512. I have multiplied it by BD. Now this value is definitely greater than what load is coming on my beam. Okay, so my concrete itself can take a shear up to 93.9 kilonewton, but the load which is coming onto the beam is only 80 kilonewton. So there is no need of shear reinforcement, but still what I will do, I will provide minimum shear reinforcement. So this is the formula for the minimum shear reinforcement. I need to find SV. So SV is coming out to be 362.78, and okay, this 362.78 it came after the provision of two leg stirrups. B I already know, point 0.4 I know, Fy I know. Only I have to assume this value, and I have assumed two leg 8 mm vertical stirrups, and next I need to give check. So this spacing, what spacing I have provided? 362. But the IS code 456 says that I cannot provide in spacing more than 195 mm. So now I have to limit further my spacing to 195 mm. Okay. So provide two legged vertical stirrups, two legged 8 mm dia vertical stirrups at 195 mm center to center. So this is the way we write the provision of stirrups in the beam. Now the next case is VU. So VU, what was the value of VU? I don't remember. Okay, 300 kilonewton. And what my beam can resist is 93.9 kilonewton. So I need to design the shear reinforcement for a value of 300 minus 93.9. So this is 206 its value. So I need to provide shear reinforcement for a shear of 206 kilonewton. I will find the spacing by using this formula, the derivation of which I have already shown you. So the spacing is coming out to be 137.6 mm for two-legged vertical stirrups of 10 mm diameter. Now I will give the checks, the maximum stirrups according to the maximum spacing for the stirrups according to IS 456. It should not be greater than 0.75 D or 300, a minimum of this value. So here I have shown you the spacing. It is okay. So this is the minimum spacing. Firstly, it is coming out to be 566. This is the minimum area of reinforcement which should be provided for the. So okay. So first, let me simplify this. This is the first spacing which I got from this formula. This is the second spacing criteria. This is first, this is second, and this is the third spacing criteria. Okay, so this spacing criteria is because of minimum area of shear reinforcement. This spacing criteria is based upon the maximum spacing for the stirrups. This spacing criteria is based upon the shear which is acting on my beam. So a minimum of all of these three cases is to be provided. So a minimum of all of these three cases is coming out to be 137 mm. So I will be providing two leg 10 mm vertical stirrups at 137 mm center to center distance. We have already seen I cannot provide any stirrups. I will ask the engineers to redesign or the designers to redesign the section. Okay, the section is inadequate to resist the factored shear force and needs to be redesigned. Now let's look at the last problem for today's class. Calculate the shear resistance of a simply supported beam of width 250 mm and effective depth 450 mm. Reinforced with 4 bars of diameter 20. All of these problems are more or less similar only. The beam is provided with shear reinforcement of two legged 10 mm. Okay, so here they are not asking me to provide design the beam for shear reinforcement, but they have already given me the shear reinforcement, and what they want me to do, they want me to calculate the shear resistance. So how will I calculate the shear resistance? Shear resistance is nothing but VUR is VUC plus VUS. I have the amount of shear reinforcement. I can calculate VUS. I know the grade of concrete and the grade of steel. So from this I can calculate VUC. The summation of both of these values will give me what? They will give me the maximum shear which is resisted by my beam. So this is simple. VUC, I need the percentage of steel, and I know the concrete and the FY415. From that I got TOSI. TOSI I will multiply it by BD. I will get VUC. Now what I will do, based upon the shear reinforcement, I will find VUS. I know FY. I know they have given me what, two left 10 mm diameter vertical stirrups. So ASV will be two times the area of this bars. B I know, SV also I know. So from here I will get VUS. I will put the values here and I will just simply add them. And this is the maximum shear which can be resisted. So the it should be minimum of all of this because we all know the shear it should not exceed above the limiting value to avoid diagonal failure. So this was all about this problem also. This I have kept you for you to calculate. I think there is nothing to calculate also. This was all about today's class. Now, also one more thing I would like you to tell. There is also one more concept in shear reinforcement, that is the concept of bent up bars. So the bent up bars usually we provide it when the amount of shear it is very high. So these are the vertical stirrups and bent up bars we provide it in this form. So bent up bars, for the design of our beam, for the bent up bars, what should I take care? This bent up bar should not take more than 50% of the shear. So even if these bent up bars are taking more than 50%, what will I do? I will restrict the shear which is resisted by these bent up bars to 50%, and I will provide the vertical stirrups for the remaining 50% of VUR. So this is also an easy concept, and you can by yourself explore or look at some problems on such bent up bars. And I have already covered some varieties of problem in this session, and I think this all would be very helpful for you. And now if you all have any doubt, you can ask me. I forgot to fill my week 5. I think that is not under my control. Is that effect on final exam? Yeah, I think you have some weightage for final exam. If you do not have some minimum marks out of the total marks of the quiz, then you won't be eligible for giving the final exam. If you miss one or two quiz, that would be fine, but I don't know what is the criteria. You can ask in the discussion forum. I am not a part of that. You should ask them whether what is the minimum weightage for you to appear in the final exam. You can ask this and know what is the eligibility criteria. So coming to the problems again, if you all have any doubt, you can ask me. This is because the stirrups it should have a minimum amount of ductility. As we go for higher grade of steels, those higher grade of steels we usually prefer it to provide for the longitudinal bars. And if my stirrups only have higher grade of steel as compared to my longitudinal steel, then that is not feasible from construction point of view also, because it is very difficult to bend this bar around these corners. So normally what we have is we usually tend to provide low diameter of bars, and the grade of steel is also kept lower as compared to the longitudinal bars. Amended means what do you mean? Yeah, yeah, I know what you are saying. See, theoretically we are like abide by many things, but when we come on to the practical construction side, people hardly follows this rule. But this IS code, like it was updated latest in 2000. You know, IS 456 2000. But you cannot abruptly change any clause and say, okay, now you cannot do this because someone is doing that. We should have some proof. Researchers are already going on, and based upon those research, a new clause, a new version of this IS code will come, which will definitely give you some more reasonable amount of grades for the stirrups, and the other changes would also come. But that's true that the many people use high, because see what generally happens, uh, the on construction side, the procurement which is done is for the similar grade of steel for the longitudinal as well as for the stirrups. So they do not take any headache to provide different grades of steel for stirrups and different grades for longitudinal bars. They like avoid to do that, but those are all the things we should control. We should have a control on as a design engineers. Close to the support means there are different cases, I think. See, what I am aware is there are different sections like this. So see, let me explain you. AV by D, this what you are saying is I am not familiar with these abbreviations AV by D. What is AV? Okay, just a second. So you are saying AV is the distance from the support. AV by D less than 1. AV by D is like let's draw this here only. So suppose this is our beam. What you are saying AV is what? No, AV is what? Just say me what is AV? Shear span. Shear span, I don't know how it will be looking into this diagram, but D will be this. Do you have any diagrammatic view? Do you have any schematic view for this? Yeah. Uh, okay, that's fine. I will figure out by my own. See, uh, are you trying to